All right. Good morning or good evening, wherever you are, to another General Zero Hour. Let's mod a General Zero Hour. Yeah, this way. Yeah, last video we dropped at W3D view memory corruption. I had the computer running because of YouTube upload over the night. I had a good sleep and ready for action. Unfortunately, Thompson's did not get back on us here on the corruption. I still have it in debugger. Yeah. Yeah, in case you didn't watch the first episode, we just mod 0 hour and you can watch and learn along the way, and hopefully you learn all the ropes to mod 0 hour one day on your own. Or just jump in, help us, help me with the work. There is plenty of work, there's infinite amount of work to make 0 hour a better game. Yeah, of course we want 0 hour to be the best game. Yeah, it needs to be stable, it needs new features, it needs to be really nice playable, smooth, high performance, beautiful. It needs to be the best game. Yeah, that's the goal. And we can only do this with hard work. Yeah, hard work. And I mean like North Korean style hard work. Really, it needs to be, you need to be up in the trenches. Yeah, hard work, hard labor. Okay, so memory corruption. So if Thompson's is not yet looking into this, he probably will at some point. But what can we do? We want to get this fixed, right? We want our tools to be stable. But it's not just tool. Like W3D View uses the game code. So it uses the code that the game would also use to, like here in this case, load the texture, right? The DXT5 DDS texture. So if there's a bug in the game code and W3D runs into a problem, then it's a legitimate problem that the game could also run into. So game also benefits if we find and fix issues in the tools. So that's actually is good. Like if all the tools are built around the original game code using it, then we also like cover like functionality of original game and make it more stable. Right? And of course there are two distinctions. There can be Thyme specific bugs, but there can also be original game code bugs that Thyme just like has because it recreates the original game, right? So yeah, there's two things. Of course, Thyme itself will have a lot of issues on its own, right, that we need to fix, make sure that we don't make mistakes. Of course, we are the best. We never make mistakes. I wish. Okay, so how do we go about this? I noticed that yesterday, as I was looking at things, I was quite confused very often. I'm not used to like look at things and then talk at the same time. I think it messes a bit, but I think I'll get used to it. So maybe sometimes I need to be a little bit quieter and just concentrate, and then you just look and I look and no talking, just quiet. Yeah, quiet, peaceful. Yeah, as if you were like, you know, with a dog, a cat on the move, everything quiet. Yeah. Just silent understanding. Yeah? Okay, so so the problem was that we have a block mem and we read from block mem, but it's invalid, right? Okay, how about this? We put a breakpoint here. I think the repro was pretty stable. Let's put a breakpoint there. So the file is unoptimized, but we are on debug anyway, so probably it's not needed. Okay, so let's start debug. We loaded CP. We need to wait first till it populates the list. CP mock. Yeah, there we go. We load all these guys here, and then we select the first. Okay, now it loads texture. Okay, let's go to our watch. Let's clean this up here. Let's type this pointer, and we are loading cbmock this 02 DDS. Okay, good. And level 0, offset 0. So it's MIP 0 probably. 16 times. It's probably like a header size, right? Of something. The 16 is a header size, I think. Do we know which one? 16. Maybe this one? 4. No, that's 32 bytes. So 4 plus 4, 8, no. 8, 16, 24, 32 bytes. Wait, we can probably see it in the code. Alpha 0. But 16 times offset is also weird. Okay, anyway, let's step over this. Yeah, so it points to the very first memory on the DDS memory. Yeah, and that is valid. Okay, let's go for the next. Now offset 16. Okay, that's all. Looks like it's also still valid. Okay, next. 32. Looks like it's also okay. 48. Also okay. 64. Also okay. 80. That is also okay. 128. It's a lot of offsets here. Oof. Okay, how about we put a breakpoint here? How about we put offset into the watch? Offset. Good. Okay, I'm seeing a pattern here as it goes really small steps. Really small steps. In 16 byte steps. Okay, now it's the next one. Okay. Level 0. Okay, well, I was hoping that we would hit some problem like early after some hits, but no. It goes through a lot of offsets. Okay. Still the same texture though. Okay. That goes through pixels each pixel. So yeah, the pixels, it goes by in 4 blocks, 4 by 4 blocks. Yeah. As a function name suggests, function name is get 4x4 block. Yeah. Okay, looks like this will take forever. Probably not the best way to look at things here. Okay, how about... Do we know how big this texture is? It's 256 times 256. Yeah, one of the problems is when we hit the crash, it's not in this call stack here, in this function, which makes like, I would like to see the values of like source X, Y, level, offset, blah, blah, whenever a corruption happens. How can we do this? Because if I press F5 now, yeah, it hits this thing, and it's, yeah, total garbage. I mean, the ASIN report is good, that looks healthy, but the crash, the call stack is bad. That's not good. Okay, how can we make it better? Okay, how about we put conditional breakpoint here. Wait, let's launch it once more. File. I have an idea. Open. CP mock. There we go. Okay, so we should be able to see how large this memory is, right? Somewhere. Okay, let's see who writes this memory. Here, data. How much is data? Data. Ugh. Do we save this data link somewhere? Or we don't? We are not saving the data. Get size of the data, accounting for header. Yeah, there's a problem with these raw allocations. Like, we can't see how big is this actually. So we probably just temporarily, let's save this. MDDS memory size. Let's make an integer. And then we just put here is data. It's a bad name here. It should be size. The name of it. Okay, it's unsigned. Okay, then let's change this to unsigned int. Okay, memory size. Yeah, let's take a look at that. Compile this bad boy. Okay. Okay, then open. If you're not familiar with programming, you see this is debugging is very draining process depending on the problem, especially memory corruption. It can be hard, but it should be solvable. If not, okay, load the first. Good. Now let's look at this. Now we see the size. Okay, that's good. So what we can probably do is we block mem. We put a conditional breakpoint here. Condition here. If block mem is larger or equal than mdds memory plus mdds memory size, like this. This way we should only hit the breakpoint if the block m is above it, and then we should be able to see exactly the point the problem occurs. Oh, it probably will be very slow, this conditional breakpoint, but it hit. Very nice. Okay, let's see. That is actually proper. Let's verify that this is actually that this is larger than our size, but it should be. Hex. Oh. Copy value. Oh. Oh, can I not copy here? Copy. So this and size this. Wait, let's take the memory in this one. So this minus this is, yeah, so this, as you can see, is, no wait, we need to go to decimal. Yeah, so 87552 is larger than 8748. Yeah, so it's definitely reading above. Yeah, okay, that's good. All right, let's say offset is 112 hundreds level 1. So it's MIP level 1. That's so. So the first MIP level is loading, and then it's above. Okay, so MIP 0, that has loaded correctly, and that's within the bounds, but MIP level 1 is not anymore. MIP level 1 is out of bounds, but that is odd. It shouldn't be out of bounds. Okay. Then I think before I proceed, let's put this into chat so that Thompsons can also see. So we have DDS memory size, and then we have block mem Okay, and I think we are interested in level and source X and source Y. Yeah. Let's load these as well. let's call this heap overflow values. This is just code. Call this custom for tests. Okay, so yeah, mip1. Okay, but that's already a lead, so we know it's mip level 1 that runs into this problem. Now let's look at DDS memory again. DDS memory. Size. Okay, so there's a file header in the DDS file and then another 4 byte. So the texture data is just whole file size minus that. I guess it's fine because down here it reads, it moves a file pointer to another question. Calculate offset for the map level we want. Okay, this I think data is not correct. What we do here. Yeah, this is not correct. Or is it? No, it is correct. It's a data. I mean, it's what it allocates. It must be correct. This, but let's see if there's some other place it allocates. No, it's the only place. Okay, good. Is the code in correct in the load function? So what if it reads too little of data? Like what if this size is just too small somehow because of this here? Let's put a breakpoint here and look at this. By the way, what file? So yeah, we crash on the first texture it loads. Okay, then let's take this. Okay. Reduction factor 0. Oh, it never goes in there. Okay. So it doesn't load the MIP level at all. What does it? It's only if it wants to load the MIP level, maybe. Yeah, that could be. So if if the DDS file is instructed to only load from a certain MIP level on and not the MIP 0, it can skip MIP levels. So it could skip level 0 or 1 or 2 and then just load the smaller MIPs, and then so that the larger texture is not even in memory, it's not loaded, right? We only load the smaller ones. Yeah, that's probably what the reduction factor does. Okay. Okay, but we load MIP 0 and then everything behind. Yeah. Okay. But then this should be, then everything should be in here. Okay, actually we can also look at the file size. Let's go to what is it loading? It's loading CP mock this. By the way, let me see. CP mock this. No, it's not loading from here. Then it's probably just loading the original texture. The original texture. CB mock this 02, this one. Properties. Can we see the exact byte size? I don't want to see kilobyte, I want to see bytes. But okay, I guess it's good enough. It's 85.4. 85.4. Uh, 85.4. That's, oh, that was correct. 85.4 times 1024. So there is 8744. Well, this rounding error. Yeah, it is close. Yeah. So, and then minus header, some size, 124. Yeah, it's in this ballpark. So yeah, it looks proper. Yeah, proper size. Okay, so this is good. And it reads. So I think this load function is correct. Let me put that also here. I think load function. Okay. Okay, then let's go back to this one. DXT5. Yeah. Good. Okay. Get width. What is this doing? Okay, that makes sense. So it is calculates the width of the next MIP level. So first MIP 0 is 256 times 256, and next MIP 1 will be 128 by 128. Yeah, and the smallest will be 4 by 4, smallest MIP level. Yeah. Okay. And now 120. I mean, this indicates to me that this is wrong, this offset thing. Memory pointer. Level offsets. Let's put that in here. The level offsets also look good to me because they're smaller than the kilobytes that we have, the bytes. So our bytes were 87400 something, right? So, and this is lower than this. So these look good to me. So my suspicion is that this calculation is wrong. Or both of these, all of this. Can you double check that the code above is proper for DXT5? Okay. Oh, yeah, let's maybe we can deduce like how it should be. I'm wondering about this times 16. Why is this there? Because this 16 is weird because like okay, so I'm trying to understand like what data is in there. So there seems to be some 16 bytes that it reads here. So the way I understand it, is 16. It looks at 16 bytes right now. So in this block mem, 16 bytes. And I try to understand this relationship of offset and 16 here. Like, how does this work? I was hoping that maybe there's some older info regarding this, because it was recently touched, this code. It seems not. Okay, we need to understand this. So, I mean, the error must be here. If it's going above the memory size, then the error must be here. Because the level offsets look okay, right? We're at level 1. Offset is 81920. No, 65536. Actually, we can also calculate if this offset is proper, right? So 256 times 256 is 65536. Yeah. Okay, so the pixels are very tightly packed. Yeah. There's no gaps in between or anything, right? So then this plus 128 times 128, that would be a MIP 0. That's the map 1. That would be the next one. And then the next one is this one. 81920. Yeah. So the MIPs are very tightly packed one after another in this chunk of data that we have, the DDS memory. Yeah. Okay, but then this also means that this makes no sense, you know? Yeah, it can't make sense. I mean, this is multiplying. It's multiplying so much. Of course it goes out of bounds. I mean, this is incredible. This can't be correct. Yeah, this can't be correct. Okay, how about I mean, this like divide by 4. Then also dividing this by 4. Is this correct? I need to understand, like, how is it loading these blocks? I mean, let's ignore this times 16s here for now. Let's just look at those 4x4 blocks. So what is happening is we're loading pixels and we move 4 pixels forward, but then it's loading the same. It should result in the same offsets for a multitude of pixels, for 4 times 4 pixels, 16 pixels. 16 pixels, aha, maybe that's what the 16 refers to. 16. That could be. I wonder if there's a division by 16 missing. Because this, if we just remove this, then I think it makes sense, because, I mean, at least from the sum, because this one, the offset will be 16 times smaller. So we divide here by 4 and here divide by 4. Actually, no, it will be even smaller, because this is also... Okay, how about we try to visualize this a bit? So we have x, 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 x. Okay, let's make this larger so we can see it. X, x, x. So this is our 4x4 block. Good. That's the first one. Now we have another one. Okay, so we are here. Let's say we are here. Here's 0, 0 pixel. X times 16. Okay, let's go with the first one. 1 times 16. 1 divided by... Let's go with another one. 2. 2 divided by 4. Maybe 1. No. 2 divided by 4. 0. Oh, okay. 2 divided by 4 is 0. Yeah, right. 2 divided by 0 times 16. Okay, how about we use these values here? 120. Okay, 120 divided by 4 times 16 plus what's the other one? 112. 112 divided by 4 times this one is level 1 6 5 5 3 6 divided by 4. Okay, let's put some here. Okay, okay, then let's 20 divided by 4, 30, yeah. 30 times 16 plus 112 divided by 4, 28 times 6 5 5 3 6 divided by 4 16 3 8 4. Okay, so add all this together. Is this 4 5 9? Huh? Did I make a mistake? Looks a bit large. Let's put this one in. Oof. Why is the number so large? Ah, get width, that's 128. This is 128. Yeah. So it's 16. 128 divided by 4, 32. Yeah. Let's dial this in. 1376. Yeah, that's the same result. Okay. Now we got it right. Yeah. Good. Does this help us to understand this? And then it does 16 times this offset. Hmm. 16 times. Oh man, I hate this. This is not fun. 16. I think Thompson may put a link here to this here. Decompress DXT5. What are they doing there? Look at this down here. Decode color block. Pixel is pixels plus x times 16 plus y times 4 times width times 4. Okay, so this is very similar to what we are doing here, but it's not quite the same. We divide block 8 bytes per block, 1 block for alpha, 1 block for color. Oh, alpha is very generous with the data. Oh. But it makes sense because DXT5 texture doubles in size with the alpha channel. Which is odd though, because alpha is just black and white. So the color pixels, they shouldn't take so much space. DXT5 format is kind of strange because the alpha channel takes so much space. Okay, but that's beside the point. Yeah, I want to understand how this decompression of this pixels work. So here, pixel x xy, walk y, walk x. Y blocks, what is y blocks? Aha, this divides by 4. width and height divided by 4. Width and height divided by 4. So this is just countering this. Yeah. Okay, so this times 4 is pretty much canceling out this division here. And this width times 4. What is width? That's times 4. We do divided by 4. Okay, so a DXT1 format, which doesn't have alpha channel, there it just looks at 8-byte chunks. Yeah, okay, so in this regard, it makes sense. There's a 16 and there's a 8. Yeah. But does the rest make sense? X times 16. X times 16. This is probably a very boring section here, but okay, maybe we should look at DDS DXT5 specification. How about that? Is that a thing? DXT5. Okay, this is block compressed. Compute the pitch. Max width plus 3 divided by 4 times block size. Block size. Compute the pitch. DDS5 DXT decompression sample. How about that? Decompression sample. No, that's not useful. Decompression algorithm. No, let's get back to this then. We x times. Okay, maybe we can try to figure out if the code in Thyme is in line with this code in principle. But the algorithm here is different because it loops over blocks here. So it increments, it starts 0, y, and then for the length of a fourth of the height and width. But here what we do is, it's different. We just calculate the offsets from input x and y. Okay. Input x and y. So we divide not the width and height by 4, but the x and y. But the thing is here, this one, y, is pretty much okay, this is x divided by 4 times 16 pixels. What is pixels? Pixels is probably, yeah, the memory pixels. So it's this. Aha. Maybe. So what I'm not seeing here is this 16 times offset thingy. Because here it's just adding it there. Pixels plus. So it's the same as like pixels bracket and then the statement. It's basically just an index into pixels. But it's not doing pixels 16 times and then this whole thing. Okay, so how about we remove this here? just for test. Let's see what happens. Maybe let's get off the conditional breakpoint by using code. If block mem DDS memory plus DDS memory size, then we want to hit just a breakpoint here of this. This will execute faster than conditional breakpoint. Conditional breakpoint is very slow. Okay, let's see what happens now. Heap buffer overflow still. Okay. Somewhere else now, but still overflowing. Okay. Let's try to get this closer to the sample implementation. So what I'm seeing here is, so X is pretty much divided by 4 because we iterate X blocks and it's divided by 4. Okay, so this we have the same. But now Y is times 4, so it is basically divided by 4 times 4. Right? Or am I mistaken? So it's like this, right? Maybe put it like this. Let's see what happens. Can't break more than it is, but this then means it goes actually larger, which is not what we want. And width is the same story. Huh. It's also weird though. Times 4. Okay, but let's go with it for now, but I expected this is even stranger. But let's go with this. Okay. Block mem. Is it? Maybe the 16 here is because of this times 4 times 4, which essentially makes it times 16. That could be. So it looks like it is actually correct. So because this to me looks like it matches here the sample implementation of this with the times 4 times 4. Yeah, maybe that's why there's 16 in there. But then why do we go out of bounds? Okay, let's remove this again here. So maybe like this. I just want a breakpoint in there. Oh, there we go. Okay. Maybe it was compiled out before because the signing to itself can be optimized away. Okay. Actually, block. What is this block here? Block. 8 bytes per block. Yeah. X plus plus. Block plus plus. Block is alpha block. Yeah. I don't really know how this is supposed to work here. One 3 times 16. That's 22,000. And that is, yeah, that looks pretty large because 65536 plus 22,000 bytes. Yeah, that overshoots here the limit. Okay, but we should be able to decipher this code. We should be able to correct this if we just understand how this works, this algorithm, which currently I don't know. It's hard to wrap my head around this. X times 16. Width times 4. Source X divided by 4. Let's go with the times 4 here once more. And remove the 16 here. Well, the good thing is when you play back the video, you can just jump forward, right? You don't need to watch me struggling here. But it's questionable if I find a solution for this. Because quite frankly, I have no clue. This DDS algorithm, I don't understand it. At least not yet. Okay, so so this actually yields different results. I mean, it still reads over limit, but somewhere else. Decode packed. So this one goes probably somewhere here. Yeah. So what we can do is if block mem how about we put plus 16? Yeah, I think like this. Larger. I think that should cover it. No, it doesn't. That's unfortunate. Okay. How can we catch this in debugger? This one. Maybe it's the DXT1 format. Maybe it's not this one. Let's put it here. If block mem is +8, put also breakpoints here. CB marked this 0 to yes. Okay. Aha, okay, so it hits this one. That's why we didn't catch the other one. Aha, okay, so this one down here no longer hits. That's interesting. But now DXT1 also still hits. That also goes over bounds and then crashes. Okay, how about here we do the same crap times 8 times 4 times 4. Well, let's double check if that's the case here. Decompress. Search for decompress txt1 here. This one is, yeah, doing it similar. X times 16. Oh, that's interesting. 4, 4, 8, 4, 4, 8. Huh. Why is there 16 here? I don't know what this refers to here. I mean, in regards to this. Okay, but this looks very different here. Okay, how about we do it times 4 here and times 4 here. Yeah. And then we move this one. Let's see what this does. Did it compile correctly? No, did not. Now it did. Okay, still hits. This is level 0. Let's see. Yeah. That's too much. Okay, let's look at the original problem. What would be good if we had like a visualization of this blocks thing. Like DDS DXT5 blocks visualization. Visualization. The blocks. Interesting. So this one is also on the MIP level, MIP 2. Okay. Yeah, something is wrong here. But it's not clear to me what. Because the other algorithms here are so much different. This is the way it does here is different. Ever so slightly. But I can't see yet exactly what the difference is. Interesting is here that there's 16, but we don't have a 16 here. This is already strange. How about we put a 16 here, but that makes it even larger. If we have a 16 here. I think we need to get a good understanding of how this memory is organized and how we access it. Okay. X blocks. So in our case, how big is our texture? 256 squared. Okay. 256 squared. X blocks is a fourth of that. Here, block. Bytes per block. Source X divided by 4. And this divided by 4. And level divided by 4. The base texture renders correctly, right? We have seen, so maybe it's only the MIP level that is wrong. Only the MIP level. Okay, let's put that back to 8. So basically the level 0 texture that renders correctly, so that then I assume that up to this point, so this and this correct, and maybe it's just this that is incorrect. But from the sample implementation, it's not clear to me if this is correct or wrong, because it's the code is just so different the way it's written. Let's go with DXT1 here. Okay, so right now I assume that this is correct and this is correct. I just make this assumption, which would leave this one as a potential source of error. Reason being, as I said before, that the MIP level 0 texture, it renders correctly in principle, right? If this was wrong, then there should be artifacts on the texture, but we don't see this. So this probably means, maybe means, that error is just with this one here. Get width level. But that also makes no sense because even MIP level 0 uses this code. So 256 divided by 4, right? And that apparently works. Okay, so this is block storage plus I times 8. This is pretty much what we do here. This one. I times 4, j times 4. I times 4, j times 4. Block counts. How about we do it similar to this? So oh, that's wrong. Right. Okay, like this. But we don't loop here. Block counts. How do we do this then? X is not sure where I'm going with this. Thing is, this thing where's it called? It's kind of odd names here. 4x4 block. I should call this. Let's rename this to X. X. This is Y. XY. So X. Man, those names. Okay, so it does it for every fourth pixel. Every fourth pixel. Don't really know what I'm doing here. Yeah, I don't know. Maybe it's better to leave that problem be for now. Because I don't quite understand what's going on here with the DDS compression. I don't understand the algorithm. I can't wrap my head around this crap. I mean, this is kind of clear. We have a 256 height and width increment by 4 pixels. And then we call get 4x4 block on this. It's kind of weird though. Why do we call 4x4 block on 4 pixels? Does that make sense? Maybe. I mean, here it does the same in principle, right? So block count is divided by 4, but then we go with xy times 4, which is pretty much the same as we do here with the plus 4, the 4 times increment. Yeah. So this looks like it's doing the same thing here. Okay. But this is different. So this is very different. Y plus J. Wow. We just need to understand this. 2 lines of code. Ignore this one. Just this and this. That's all. Oh, how hard can it be? How hard can it be? Let's remove this. This is garbage. Yeah, I'm struggling with this. I have to admit. Okay, we know that we pass x, so x will be x will be 0, 4, 8, and so on, right? And this one as well. Y also 0, 4, 8, 12, 16, 20, and so on, right? And then we divide that by 4. Which gets a block pretty much. Divided by 4 is a block. Yeah. But then y times 8 times 8. I don't know. Maybe because of this times 8. X blocks. Yeah, so this is x blocks pretty much. Okay, how about we rename this? Make a int x block. X block. Let's do it like this. So we refactor a bit so it's easier to understand. This is x block. Then we have y block. Y block. This. Y block. Okay. So x block times 8. So this is also what we see here. I can do all block or block count. Block count. And this is, but it's only x block counts. Okay, does this help us in understanding? Probably not. X block. X times 16. We don't have a 16 here. Y times 4. Also don't have that. Pixel. How about we block mem? Maybe this refers just to like this thing. How about we just do it like it does it here? So y What is y? Y is... Who's calling this? Can't see. Huh. Y. Ah, what is Y is a block. Y. Okay, how about we let's comment this. Let's comment this as well. This y times x blocks. So y is y divided by 4. Right? That is, so is y. So is y divided by 4 times x blocks. X blocks is this one. X blocks with divided by 4. Okay, let's roll with that. And this times 8. That's what this is doing, right? Well, let's see what this does. I'm desperate. I will just try now. Try and error. Let's see. It doesn't make a whole lot of sense to me because now we have no x. X is doing nothing. Like that's really odd. Pixel block mem. But okay, let's go with this for now. Let's see what this does. Probably doesn't work. That looks, I mean, it doesn't crash, but it also doesn't look good. Yeah. Okay. Yeah, texture's just black. Okay. Okay, so this is wrong as well, but at least it doesn't crash, so it's better than what it was before. Well, it's not hard. It's not hard. Okay. Yeah, so this is just black. Yeah, it's a problem. I don't understand this algorithm. I think that's a conclusion for now. Yeah, I think this was a bit of a waste of a time. I'm not any wiser. Congratulations if you watched this far. You're probably also none the wiser. Unless you understand the DDS algorithm and you look at me looking at this and say, what the fuck is he doing? Which I cannot fault you for. Yeah. Okay, but I have no clue right now how this is supposed to be written. My hope is that Thompsons can take another look at the original code, make a comparison, and figure out the difference, what is wrong. Because clearly there is something wrong. We are reading over the bounds of the memory buffer. That's clear. That is the problem. But I have no clue how to write this algorithm that it actually works correctly. Because this implementation is custom. I have great difficulties to compare it with other implementations that maybe work, I hope. So yeah, I don't know what to access. I would need to study more. I would need to like really understand like, okay, how does this all work? But I don't understand this. It's a lot. It's a lot. Yeah. But what we can maybe do is with a bit trial and error. How about let's revert this. Oh. Let's revert all the changes we did here. So let's remove this one here, just for fun. And we have this one removed. Put breakpoint in here. Breakpoint in here. Let's just load this one here. Okay, so now still black. All textures are black. But at least it doesn't crash. That's something. Okay, let's maybe try and error is not a bad approach here to reduce some numbers and then see if we get some proper results. That's maybe actually not a bad idea. Okay, so this one hits DXT1. Yeah. DXT1. Level 2 again. MIP2. Yeah, no, it doesn't make sense. Try and error is stupid. Okay, I leave it at that. I don't know what to do right now with this. Yeah, it's unfortunate, but yeah, I don't know how to approach this for now. I hope that Thompson has some answers. Otherwise, yeah, I would need to study this, and this takes a while because it's quite some intense code here. Yeah. Okay, then I will cut the video for now and eat something, and then afterwards return with some more productive work, I think. Yeah. Well, it was, I think, not a good video, but okay, it's part of the process. Sometimes we get stuck and we look at things, we don't know what to do. And this is one of these cases. I have no clue what I'm doing, and that's about it. All right.